Hello there, and welcome to the Sleepy Science Channel. The world outside can be busy and loud, but here, things slow down. Tonight, we're not gazing at mountains, rivers, or the night sky. We're slipping into a hidden realm, where a single photon can travel like a wave, yet act like a particle, where atoms can communicate across the vastness of space, and even the emptiest vacuum bubbles with energy. We'll travel gently, through quantum fields, teleporting particles, and moments when the act of perceiving changes what exists. Some of what you hear tonight may puzzle you. Some may stay with you, like the trace of a dream you can't quite explain. And just before we begin, if these calm, curious explorations help you unwind, or give you a quiet way to end your day, consider liking and subscribing. Or simply share your thoughts in the comments below. It helps others find their way here too, one sleepy soul at a time. Now, if you're ready, let's begin. The rules of physics change dramatically at tiny scales. In our everyday world, physics feels dependable. Apples fall, clocks tick, light travels in straight lines. But shrink your view down to the size of atoms, and those familiar rules begin to twist. At the quantum scale, particles don't always move in predictable paths. They follow probabilities, behaving more like hazy clouds than solid dots. Causes and effects don't line up in the neat, linear way we expect. Events can seem to happen without clear reasons, and sometimes two possibilities unfold side by side until something forces a choice. This strange shift from the predictable to the probabilistic is why quantum physics feels like a different universe hiding within our own. It's not that the everyday rules break, it's that they were never the whole story. Beneath them lies a stranger, softer framework that holds everything together in ways we're only beginning to understand. Quantum physics governs a world unlike anything we see. Most of us will never directly see the quantum world. Its smallest building blocks are far tinier than the wavelength of visible light, so they remain forever hidden from our eyes. Yet their behavior shapes everything we touch, breathe, and become. In this unseen realm, particles drift like ripples in a pond, pop into existence for fleeting moments, and sometimes act as though they're in several places at once. The rules here are written in mathematics so unusual that even seasoned physicists often admit they use the equations without claiming to fully grasp their meaning. This isn't just a smaller version of our reality, it's a fundamentally different one, operating on principles that defy our common sense. And yet, without this invisible world quietly playing out its patterns, the visible universe, including us, could not exist. Energy is not continuous. It comes in tiny packets. In the late 1800, scientists thought energy was smooth, like water flowing from a tap. Then came the shock. Under certain conditions, it's not smooth at all. Light, heat, and other forms of energy are made of tiny, indivisible quanta. A quantum is the smallest amount of energy a system can gain or lose, like the smallest coin in the currency of the universe. This discovery, sparked by studies of how light interacts with matter, overturned centuries of physics. It explained why heated objects glow in the colors they do, why atoms absorb and release light in narrow bands, and why energy can sometimes feel like it appears in discrete jumps instead of steady flows. Without this idea, known as quantization, modern technology from lasers to computers wouldn't exist, and the doorway to quantum theory might never have been opened. Matter can flow like a wave, yet strike like a particle. It sounds impossible. How can something be both a wave and a particle? But that's exactly how quantum objects behave. Shine light through two narrow slits, and it spreads into rippling interference patterns, a hallmark of waves. but detect the light particle by particle, and each one lands at a single point, like a tiny bullet. The same is true for electrons, atoms, and even some large molecules. This wave-particle duality suggests that particles don't travel as tiny billiard balls, but as probabilities smeared out across space until they're observed. Then their wave-like spread collapses into a definite location. This strange dual identity isn't just an oddity, it's at the heart of quantum mechanics. It means that what we think of as solid and localized is, in truth, part of a larger, fluid pattern that only sharpens when we look. Simply watching can change how reality unfolds. In the quantum world, observation is not passive. The very act of measuring a particle can change its state. In the famous double-slit experiment, photons or electrons form wave-like patterns when left alone, but switch to particle-like behavior when their paths are observed. It's as if nature knows when we're watching, though physicists explain it as the unavoidable interaction between the measuring device and the system. Still, this raises profound questions. If every measurement alters reality, then what is reality before the measurement? Is the world in a fuzzy in-between state until something forces it to choose? Whether you see it as a physical process or a philosophical puzzle, the idea that observation changes the outcome is one of the most mind-bending truths of quantum mechanics, and one that has fascinated and unsettled scientists for over a century. Nature forbids us from knowing everything about a particle. Classical physics promised that if you measured precisely enough, you could know everything about a system, its position, speed, future path. Quantum mechanics says otherwise. The Heisenberg uncertainty principle tells us that there are limits to what we can know at the same time. For example, the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This isn't a flaw in our instruments. It's a built-in feature of nature itself. Particles simply do not have exact values for certain pairs of properties at the same time. The uncertainty is real and unavoidable. This means that, at the quantum level, the future can never be predicted with perfect accuracy. All we can do is calculate probabilities, a shift in thinking that transformed science and challenged our deepest assumptions about determinism. A particle can exist in many states at once. Superposition is one of the strangest concepts in quantum physics. The idea that a particle can exist in multiple states or locations at the same time. An electron can spin up and down simultaneously, or a photon can take several paths at once. These states exist in a delicate balance described by a mathematical wave function. Only when a measurement is made does the particle choose one outcome, and the superposition vanishes. This isn't just theory. Experiments confirm it again and again. Quantum computers exploit superposition to perform many calculations in parallel, giving them immense potential power. In everyday life, superposition is impossible to see directly because it collapses the moment we interact with it. Yet at the quantum scale, it is the norm, a reminder that our everyday reality is just one version pulled from a swirling cloud of possibilities. Reality is built from probabilities, not certainties. In the quantum realm, nothing is certain until it happens. A particle's position, momentum, or spin isn't fixed ahead of time. It's described by a set of probabilities. These probabilities are encoded in the particle's wave function, which evolves smoothly until an interaction or measurement occurs. Only then does one outcome emerge, chosen seemingly at random from the possible ones. This probabilistic nature is not due to ignorance, but is fundamental to the way the universe works. Even with perfect knowledge of the wave function, you can only predict likelihoods, never guarantees. This was unsettling to many physicists, including Einstein, who famously said, "God does not play dice with the universe." But over a century of experiments has shown that, at the smallest scales, probability isn't a sign of incomplete knowledge. It's reality itself. How possibilities collapse into reality is still a mystery. We know that a quantum system can exist in many possible states at once, and that measurement somehow reduces these possibilities to a single outcome. But exactly how this collapse happens, or if it's even real, remains one of the biggest puzzles in physics. Some interpretations suggest collapse is a physical process triggered by observation. Others claim that all possibilities happen, but we experience only one branch of a larger multiverse. Another view says collapse is just an illusion, and the wave function never truly reduces at all. Despite decades of debate, no consensus exists. What's certain is that this moment, the shift from many possibilities to one, is central to our experience of reality. Understanding it may require not just new physics, but a deeper grasp of the nature of consciousness and the limits of knowledge. Schrödinger's cat is alive and dead until you look. In 1935, physicist Erwin Schrödinger proposed a thought experiment to show how strange quantum superposition can be when applied to everyday objects. Imagine a cat in a sealed box with a device that has a 50-50 chance of releasing poison based on the decay of a single atom. Quantum theory says the atom is in a superposition of decayed and not decayed until measured, and so, in principle, the cat is both alive and dead at the same time. Only when you open the box does the superposition collapse into one outcome. Schrödinger didn't mean we should take this literally for cats. He meant to highlight the absurdity of quantum rules in the macroscopic world. Yet his famous cat remains one of the clearest, most enduring ways to picture the weirdness of quantum mechanics. Two particles can share the same existence across space. Entanglement is one of the most baffling features of quantum mechanics, a phenomenon where two particles become so deeply linked that their states are no longer separate. Measure one, and the other's properties snap into place instantly, no matter how far apart they are. It's as though they're not two particles at all, but one system stretched across space. This connection doesn't fade with distance, and it doesn't rely on signals traveling between them in the normal way. Once entangled, the particles share a kind of joint identity. Physicists have created entanglement in labs with photons, electrons, and even small groups of atoms. It's a fragile link, easily broken by outside interference, yet when preserved, it hints at a deeper layer of reality, one where separation is an illusion and the universe is more interconnected than we can see. Touch one particle here, and another responds instantly far away. If you take two entangled particles and send them to opposite sides of the planet, something extraordinary happens. Measuring one instantly determines the state of the other. This happens even if they're so far apart that light, the fastest thing in the universe, couldn't carry a message between them in time. It's not that information travels faster than light. Rather, the two particles don't have independent states to begin with. They are, in a sense, the same thing. This instantaneous connection has been tested again and again in laboratories, with distances stretching from meters to hundreds of kilometers. The results always match quantum theory's predictions, no matter how counterintuitive they seem. It's a reminder that our everyday notions of cause, effect, and distance may not apply in the deepest workings of nature. Even Einstein was disturbed by this quantum link. Albert Einstein famously disliked the idea of entanglement. He called it spooky action at a distance, convinced that it must be an incomplete description of reality. In his view, there had to be hidden variables, unseen factors that would explain the strange correlations between particles without invoking faster-than-light effects. Along with Boris Podolsky and Nathan Rosen, he proposed a thought experiment in 1935, now known as the EPR paradox, to challenge quantum mechanics. They argued that if quantum theory was correct, it implied either impossible communication between distant particles, or that the particles didn't have definite properties until measured, both of which felt absurd. Decades later, experiments proved that entanglement is real and cannot be explained by hidden variables alone. Ironically, Einstein's own challenge helped inspire the research that confirmed quantum mechanics' most mysterious feature. Experiments show this connection is real and unbreakable. For decades, entanglement remained a theoretical puzzle. Then, starting in the 1970s, physicists began designing experiments to test it directly. Using pairs of photons, they measured the correlations between them and compared the results with the predictions of quantum mechanics versus classical hidden variable theories. The results were decisive. Quantum mechanics won. Since then, the tests have grown ever more precise, closing loopholes and extending the distances between entangled particles. In 2017, scientists sent entangled photons between ground stations and a satellite in orbit, confirming the effect over more than 1,000 kilometers. Each success strengthens the conclusion: entanglement is not just a quirk of the lab, it's a fundamental feature of reality. And as strange as it seems, the universe allows this perfect connection to exist without any visible link at all. No hidden mechanism explains these strange correlations. Einstein hoped that entanglement could be explained by hidden variables, secret information carried by particles that predetermines their behavior. But in the 1960s, physicist John Bell devised a mathematical test to tell whether such variables could exist. His result, known as Bell's theorem, showed that if hidden variables were real, the correlations between entangled particles would be limited in specific ways. Quantum mechanics predicted stronger correlations, and experiments consistently found them. This means that no theory relying solely on hidden local information can fully explain what's happening. The universe, at its core, doesn't behave according to the tidy, deterministic rules Einstein envisioned. Instead, it behaves in a way that suggests reality is more deeply connected and perhaps less local than we ever imagined. Bell's theorem proved the universe doesn't behave classically. Bell's theorem is one of the most profound discoveries in physics. It doesn't just say that quantum mechanics is weird. It says that if the theory is correct, then the universe itself cannot be explained by any classical model that relies on local causes. The fact that experiments match quantum predictions means that nature either allows instantaneous influences across distance, or it abandons the idea that objects have definite properties before we measure them. Either way, it forces us to rethink what's real and how reality is structured. Bell's work, once a niche subject, has now become central to quantum information science, laying the groundwork for technologies like quantum cryptography and secure communication, all built on the very spooky TEEN, action that Einstein doubted. Quantum teleportation sends a particle's identity elsewhere. Quantum teleportation isn't like science fiction. It doesn't move objects through space in an instant. Instead, it transfers the state of one particle to another, using entanglement as the bridge. First, two particles are entangled. One is sent to the destination, while the other stays with the sender. By performing a special joint measurement on the sender's particle and the particle to be teleported, the quantum state is destroyed in one place and recreated in the other. No physical matter travels, but the exact quantum information does. This process has been demonstrated with photons, atoms, and ions over distances ranging from a few meters to hundreds of kilometers. It's a key ingredient for building quantum networks, and though it won't beam humans across space, it does something equally magical. It lets the identity of a quantum system leap from one location to another. Some think spacetime emerges from entanglement. In recent years, a bold idea has gained attention, that the very fabric of spacetime might be woven from quantum entanglement. According to this view, the geometry of space, the distances, curves, and connections between points, could be the large-scale expression of countless microscopic quantum links. If true, this would mean that gravity and the shape of the universe are not fundamental, but emerge from a deeper layer of quantum information. Theoretical studies in areas like holographic duality and tensor networks hint at how such a connection might work. While still speculative, this idea could unite general relativity and quantum mechanics into a single framework and reveal that without entanglement, space itself might unravel. The universe may be woven together by quantum links. If entanglement is as universal as quantum theory suggests, then it's not just a laboratory oddity, it's happening everywhere, all the time. Particles produced together in distant stars, ancient cosmic events, or even the Big Bang itself may still be connected by invisible threads. In this sense, the universe is less like a collection of separate objects and more like a single, seamless whole. These connections may fade when disturbed, but new ones form constantly as particles interact. The idea that reality is stitched together in this way challenges the picture of the cosmos as a vast emptiness dotted with isolated points of matter. Instead, everything may be part of a single, ongoing quantum conversation, written in the shared language of entanglement. Entangled particles can keep their bond against all odds. Entanglement is delicate. It can be destroyed by heat, noise, or interactions with the environment. Yet in some conditions, it can persist in surprising ways. Certain systems, like superconductors and Bose-Einstein condensates, can hold vast numbers of particles in entangled states that endure for long periods. Even in the messy, noisy world outside the lab, traces of entanglement have been observed between particles separated by significant distances. This resilience makes entanglement not just a fragile curiosity, but a potential resource for real-world technologies. If we learn to protect and control it, we could harness these enduring bonds to power quantum communication, computing, and sensing on a scale that transforms how we share and process information. Electrons are infinitely small yet spread out like clouds. An electron is one of the most familiar subatomic particles. It flows through wires, binds atoms together, and shapes the chemistry of life. Yet when scientists try to measure its size, they find something baffling. It behaves as if it has no internal structure and no measurable diameter. At the same time, it doesn't act like a pinpoint. Instead, its presence is smeared out in a cloud of probability, surrounding the atomic nucleus in patterns shaped by quantum rules. This electron cloud isn't a physical fog, but a map of where the electron is most likely to be found. In one moment, it might be near the nucleus, in the next, far away, and it's impossible to predict exactly where until you look. This dual nature, both point-like and spread out, is a perfect example of how quantum particles defy our everyday intuition. Weightless photons can still push objects around. Photons, the particles of light, have no mass, yet they carry energy and momentum. This means they can exert pressure when they strike an object, a phenomenon known as radiation pressure. In space, where there's no air to resist movement, this tiny push can have a big effect over time. Sunlight can slowly alter the paths of dust grains, asteroids, and even spacecraft. Engineers have even designed solar sails, vast mirror-like sheets that use the momentum of sunlight to propel them, requiring no fuel at all. On smaller scales, focused beams of light can trap and move microscopic objects. A technique called optical tweezers which is used in biology and nanotechnology. That something with no rest mass can physically move matter is one of light's most surprising and useful quantum gifts. Billions of ghostly neutrinos pass through you every second. Every moment, without you feeling a thing, countless neutrinos are streaming through your body. These nearly massless particles are created in enormous numbers by the sun, distant stars, exploding supernova, and even radioactive decay in Earth's crust. Neutrinos interact so weakly with matter that they can pass through entire planets as if they were empty space. Trillions of them are flowing through Earth, and you at any given moment, yet detecting them is incredibly difficult. Huge underground detectors filled with ultra-pure liquids or ice wait patiently for the rare event when a neutrino collides with an atom. Studying them can reveal secrets about how stars work, how the universe evolved, and even whether matter and antimatter are perfectly symmetrical. Invisible, almost intangible, neutrinos are proof that the cosmos is full of hidden motion and energy we barely notice. Quarks are forever trapped in groups of 2 or 3. Quarks are the fundamental building blocks of protons and neutrons, and therefore of most of the matter we see. But unlike electrons, quarks are never found alone. They are confined by the strong nuclear force, mediated by particles called gluons. This force grows stronger as quarks are pulled apart, much like stretching a rubber band that resists more and more. Try to separate quarks, and the energy you add will eventually create new quark pairs, which immediately bind into new particles. This phenomenon, known as confinement, means that quarks are forever locked together in groups of 2 mesons or 3 baryons. It's as if nature has decreed that quarks can never be solitary travelers. They exist only as parts of a greater whole, bound in the heart of every atom's nucleus. Gluons hold the strongest bonds in the universe. The strong nuclear force is the most powerful of nature's 4 fundamental forces, and gluons are its carriers. Their name comes from their role, gluing quarks together to form protons, neutrons, and other particles. But gluons are unlike the force-carrying particles in electromagnetism or gravity. They not only interact with quarks, but also with each other, creating a dense, self-binding network that traps quarks inside. This makes the strong force so intense that breaking a single proton apart would require energies far beyond anything we can produce on Earth outside of particle accelerators. Without gluons, atoms and the matter they form could not exist. In a very real sense, gluons are the hidden threads that keep the universe stitched together at its smallest scales. Without the Higgs boson, mass would not exist. The Higgs boson, discovered in 2012 at CERN Large Hadron Collider, was the missing piece of the standard model of particle physics. It's associated with the Higgs field, an invisible energy field that permeates all of space. As particles move through this field, they interact with it, and this interaction gives them mass. Without the Higgs field, particles like quarks and electrons would have no mass, and atoms, planets, and life could never form. The Higgs boson itself is a quantum ripple in the Higgs field, detectable only in high-energy collisions. Its discovery confirmed a decades-old theory and earned François Englert and Peter Higgs the Nobel Prize. It also provided a profound answer to a simple question: why does anything weigh anything at all? Empty space boils with fleeting virtual particles. Even in perfect vacuum, space is not truly empty. Quantum field theory predicts that pairs of particles and antiparticles constantly flicker into existence, borrowing energy from the vacuum before annihilating and disappearing again. These virtual particles can't be observed directly, but their effects can be measured. For example, they cause tiny shifts in the energy levels of electrons in atoms and produce forces between objects in vacuum, known as the Casimir effect. This constant bubbling of activity means that empty space is more like a restless ocean than a still void. The idea that nothing is actually full of temporary, unseen particles is one of the strangest and most confirmed predictions of quantum physics. The quantum vacuum is bursting with energy. All those fleeting virtual particles in the vacuum carry energy, called zero-point energy, that exists even when a system is at its lowest possible energy state. In principle, every cubic centimeter of empty space contains an enormous amount of this energy. Most of it cancels out or remains inaccessible, but its effects can still be detected in subtle ways, such as in the behavior of atoms and the expansion of the universe. In cosmology, some scientists suspect that dark energy, the mysterious force driving cosmic acceleration, may be linked to vacuum energy. The paradox is that theoretical calculations predict a vacuum energy vastly larger than what we observe, suggesting we still don't fully understand one of the most fundamental ingredients of reality. Antimatter is matter's perfect, but opposite twin. For every type of particle, there exists an antiparticle with the same mass but opposite charge and other properties. When a particle meets its antiparticle, they annihilate in a burst of pure energy. Antimatter was predicted by Paul Dirac in 1928 and discovered in cosmic rays soon after. It's rare in the universe today. Most was destroyed in mutual annihilations shortly after the Big Bang. Why matter survived while antimatter mostly vanished remains one of the great unsolved mysteries of physics. We can create antimatter in particle accelerators and even trap small amounts. But storing it is challenging because it annihilates on contact with matter. Antimatter isn't just a curiosity. It has potential applications in medicine, such as in PET scans, and in future propulsion systems that could, in theory, harness its incredible energy density. Matter can be created from pure energy and erased back. Einstein's famous equation, E equals mc2, tells us that mass and energy are two forms of the same thing. Under the right conditions, energy can transform into matter, and matter back into energy. High-energy collisions, like those in particle accelerators or near black holes, can produce particle-antiparticle pairs from pure energy. Conversely, when particles meet their antiparticles, they annihilate into photons. This constant interchange between mass and energy plays out throughout the cosmos, in the hearts of stars, in the early universe, and in extreme astrophysical events. It shows that matter isn't a permanent solid substance. It's a form energy can take, briefly shaped into particles before returning to light. Every particle is just a ripple in an invisible field. According to quantum field theory, the universe isn't made of particles floating in empty space. It's made of underlying fields that stretch everywhere. Each type of particle is simply a localized vibration, or ripple, in its own field. Electrons are ripples in the electron field, photons are ripples in the electromagnetic field, and so on. Even when there are no particles present, the fields themselves still exist, filling all of space. This way of thinking unites matter and energy, showing them as different expressions of the same underlying fabric. It also means that particles aren't tiny, indivisible marbles. They're events, disturbances in something deeper and more fundamental. Wherever you are, these invisible fields are right there, quietly shaping everything you see, touch, and experience. Quantum field theory merges particles and forces into one. Before quantum field theory, particles and forces were treated as separate things, objects that interacted through invisible influences. But QFT revealed that forces themselves arise from fields, and their effects are carried by particles. In electromagnetism, for example, the electromagnetic field produces photons, which mediate the force between charged particles. The strong nuclear force emerges from the gluon field, and the weak nuclear force from the W and Z boson fields. Even gravity may one day be described this way, though a complete quantum theory of gravity still eludes us. QFT is one of the most successful frameworks in all of science, with predictions confirmed to extraordinary precision. It's our best description of reality at the smallest scales, a single language for both the matter that exists and the forces that move it. Even the emptiest space is alive with activity. If you imagine the vacuum of space as cold, empty nothingness, quantum physics invites you to think again. Even without particles, fields are never perfectly still. They quiver with constant fluctuations, producing brief appearances of virtual particles that vanish as quickly as they arrive. This restless background is present everywhere, between the stars, inside atoms, even in the vacuum of your living room. It's an energy that can't be turned off, and though most of it is hidden, it leaves measurable fingerprints in experiments. The fact that nothing is actually a seething, active medium changes the way we think about space. It isn't an empty stage for reality to unfold on, it's part of the cast, quietly shaping the drama at every moment. A perfect vacuum can pull objects together. It sounds like science fiction. Place two uncharged metal plates very close together in a vacuum, and they will slowly drift toward each other. This is the Casimir effect, a direct consequence of quantum vacuum fluctuations. The space between the plates allows only certain wavelengths of virtual particles to exist, while the space outside allows more. This difference in pressure pushes the plates inward. The effect is incredibly small, but it's been measured in laboratories and confirms that the vacuum isn't empty at all. Though it has no practical use yet, the Casimir effect is a striking reminder that quantum forces can emerge from what we think of as nothing, shaping the motion of real, physical objects. Zero-point energy exists everywhere in the universe. Even when a system is in its lowest possible energy state, with no heat, no motion, no light, it still contains a residual amount of energy called zero-point energy. This is a direct result of the uncertainty principle. You can't have a field with zero energy, because that would mean knowing both its position and momentum exactly. Zero-point energy is tiny on human scales, but because it exists everywhere, it may add up to something enormous across the cosmos. Some theories suggest it could be linked to the mysterious dark energy driving the universe's accelerated expansion. Whether or not that's true, zero-point energy is one of the clearest examples of how quantum physics says empty space is never truly empty. Empty space can warp gravity and time. In Einstein's theory of general relativity, mass and energy tell spacetime how to curve, and curvature tells matter how to move. If the vacuum is full of quantum energy, then even empty space can shape the geometry of the universe. This means that quantum effects may subtly influence gravity, and perhaps time itself. In principle, the density of vacuum energy could change how the universe expands, how galaxies form, and even how time flows in extreme conditions. The exact nature of this interaction is still a mystery, partly because combining quantum theory and gravity into a single framework remains one of the hardest problems in physics. But it's possible that the key to understanding cosmic evolution lies hidden in the structure of empty space. Powerful fields can twist the nature of the vacuum. The vacuum might feel unchangeable, but under extreme conditions, it can transform. Very strong electric or magnetic fields can polarize the vacuum, aligning its virtual particles in ways that alter its properties. In theory, if the fields are intense enough, they could even cause the vacuum to break down, producing real particle-antiparticle pairs out of the energy. This phenomenon, called vacuum decay, hasn't been observed directly. The required fields are beyond anything we can currently generate, but its effects are predicted by quantum electrodynamics. Such behavior means that the vacuum is not a passive backdrop, but an active, dynamic medium that can respond to its environment in surprising ways. Black holes glow by stealing energy from empty space. Black holes are famous for letting nothing escape, not even light. Yet quantum theory predicts that they can slowly radiate energy, a process called Hawking radiation. Near the event horizon, vacuum fluctuations constantly create pairs of virtual particles. Normally, these particles annihilate quickly, but at a black hole's edge, one particle can fall in while the other escapes. To an outside observer, it looks as though the black hole is emitting radiation, slowly losing mass over time. This process is incredibly faint for large black holes, but it's a profound insight. Quantum physics suggests that even the darkest, most inescapable objects in the universe are not completely black. The energy of nothingness may be driving the universe apart. In 1998, astronomers discovered that the expansion of the universe is accelerating. The cause is unknown, but one leading candidate is dark energy, a form of energy that seems to be built into space itself. If dark energy is real, it behaves much like vacuum energy, exerting a constant outward pressure. Over billions of years, this force could stretch the universe so far that distant galaxies slip forever beyond our reach. The idea that the ultimate fate of the cosmos might be determined by the energy of empty space is one of the most haunting results to come from modern physics. The true nature of the quantum vacuum remains unknown. We can describe the quantum vacuum mathematically, measure its effects in experiments, and even connect it to cosmic scale phenomena. But we still don't truly understand what it is. Is it a physical medium, like an invisible ocean filling space? Is it a property of fields that exist whether or not particles are present? Or is it something even stranger, perhaps tied to the origin of the universe itself? The vacuum sits at the intersection of quantum theory, relativity, and cosmology, three pillars of physics that still resist full unification. Until we understand it completely, the emptiness between the stars will remain one of the most profound and mysterious aspects of reality. Quantum computers can think in many realities at once. Unlike classical computers, which process information in binary bits that are either 0 or 1, quantum computers use qubits, units that can exist in superpositions of 0 and 1 at the same time. This allows them to explore many possible solutions simultaneously, as if they're testing outcomes across multiple realities before settling on an answer. The power of this approach grows exponentially with the number of qubits, making certain problems that would take classical computers millennia potentially solvable in seconds. Quantum computers are still in their infancy, struggling with error correction and stability, but even now they hint at a future where problems in chemistry, cryptography, and optimization could be cracked with breathtaking speed. It's not magic, it's the quantum rules of probability and interference, harnessed in a way that classical logic could never match. Qubits can store multiple answers in a single moment. A qubit isn't locked into a single state until it's measured. Before then, it can hold a blend of possibilities, both 0 and 1, weighted by probabilities. This property is what gives quantum computers their massive potential power. With just a handful of qubits, you can represent an astronomical number of possible combinations at once. When a quantum algorithm runs, it manipulates these probabilities in a carefully choreographed way, so that the wrong answers cancel each other out and the correct one remains. It's like searching an entire library in parallel instead of book by book. The catch is that measurement collapses a qubit state, so designing algorithms that extract useful results from this delicate superposition is one of the central challenges in quantum computing. Entanglement supercharges quantum processing. Entanglement isn't just a curiosity, it's a resource. In quantum computing, entangled qubits share correlations that classical bits never could, allowing operations on one qubit to instantly influence its entangled partners. This enables quantum computers to perform complex computations more efficiently, linking distant parts of a problem together without moving physical information around. Entanglement also plays a role in error correction, helping detect and fix mistakes without directly observing the qubit's fragile states. Without entanglement, quantum computers would lose much of their advantage over classical machines. It's the invisible thread that ties their logic together, giving them the power to tackle problems far beyond the reach of today's fastest supercomputers. Certain quantum algorithms could solve problems instantly. Some quantum algorithms are so efficient that they could, in principle, crack problems that would stump classical computers for centuries. One famous example is Shor's algorithm, which can factor large numbers exponentially faster than the best-known classical methods, a breakthrough that could undermine many of today's encryption systems. Another is Grover's algorithm, which can speed up database searches in a way no classical approach can match. These algorithms don't make quantum computers universally faster, but for the problems they are suited to, the advantage can be enormous. This is why governments, tech companies, and researchers are racing to develop practical quantum processors. The first to do so will unlock computational capabilities that could reshape technology and security. Quantum cryptography creates secrets that can't be cracked. Classical cryptography relies on the difficulty of certain mathematical problems, but in theory, a powerful enough computer could break them. Quantum cryptography, by contrast, uses the laws of physics to guarantee security. The most famous method, quantum key distribution (QKD), sends encryption keys encoded in the states of photons. Any attempt to eavesdrop inevitably disturbs these states, revealing the intrusion instantly. This means that secure communication is possible even over channels an attacker can fully observe. Quantum cryptography has already been tested in real-world networks, including satellite links, and could one day protect financial transactions, government communications, and personal data with a level of keen security no classical system can match. Quantum sensors detect the barest whispers of change. By exploiting quantum effects like superposition and entanglement, quantum sensors can measure quantities such as time, acceleration, and magnetic fields with extraordinary precision. They're so sensitive that they can detect changes too small for any classical instrument, shifts caused by tiny gravitational variations, subtle brain activity, or even the presence of dark matter particles. Some designs use clouds of ultra-cold atoms or nitrogen vacancy centers in diamond to achieve this sensitivity. In the future, quantum sensors could revolutionize navigation, medical imaging, and geological surveying, opening new windows into both the human body and the Earth itself. Superconductors let electricity flow forever without loss. Normally, electric currents face resistance, converting some of their energy into heat. But in certain materials cooled to extremely low temperatures, resistance drops to zero, a state called superconductivity. In this state, electrons pair up and flow without losing any energy, potentially forever. This phenomenon is quantum in nature, relying on the collected behavior of countless particles, acting as a single, coherent wave. Superconductors are already used in MRI machines, particle accelerators, and magnetic levitation trains. But if we could achieve superconductivity at room temperature, it would revolutionize energy transmission, eliminating waste and enabling entirely new technologies. Quantum networks could connect computers across the globe. Just as classical computers are linked by the internet, future quantum computers could be joined by quantum networks. These networks would use entanglement and quantum teleportation to transmit information in a way that's impossible to intercept without detection. Building such a network requires creating and maintaining entanglement over long distances, something researchers are already testing using optical fibers, satellites, and quantum repeaters. A fully functional quantum internet could enable ultra-secure communications, distributed quantum computing, and new forms of sensing that work across vast distances, essentially turning the entire planet into a single, interconnected quantum system. Atomic clocks keep time so well they barely drift in billions of years. The most accurate timepieces in the world are atomic clocks, which use the natural vibrations of atoms, often cesium or ytterbium, as their ticks. In advanced versions, atoms are cooled to near absolute zero and held in place by lasers, allowing their oscillations to be measured with incredible precision. The best atomic clocks would gain or lose less than a second over the entire age of the universe. Such precision isn't just academic. It's crucial for GPS navigation, telecommunications, and scientific experiments. Quantum advances are pushing this accuracy even further, to the point where atomic clocks might soon detect changes in the passage of time caused by tiny differences in gravitational potential. Quantum technology is already reshaping science. While quantum computers often grab headlines, quantum technology is already at work in many areas of research and industry. Quantum sensors are mapping underground structures, quantum communication links are securing test networks, and quantum simulators are helping scientists model complex molecules and materials. These tools aren't science fiction. They're practical applications of quantum mechanics that are expanding our capabilities today. As the technology matures, it's likely to influence fields from climate modeling to drug discovery, giving us new ways to understand and shape the world. The quantum revolution isn't coming someday. It's already here, quietly changing the way we explore reality. The Copenhagen interpretation says reality isn't real until measured. The Copenhagen interpretation, developed in the 1920s by Niels Bohr and Werner Heisenberg, remains one of the most widely taught explanations of quantum mechanics. It suggests that a quantum system doesn't have definite properties until it's measured. Before that moment, it exists in a superposition, a blend of all possible outcomes. The act of measurement forces the system into a single state, collapsing the wave function. This view is practical, matching experimental results perfectly, but it's philosophically unsettling. Does reality truly depend on observation to exist in a definite form? Or is the collapse just a mathematical shortcut we use because we can't track every quantum detail? The Copenhagen interpretation leaves these questions open, accepting uncertainty as a fundamental part of the universe, not a flaw to be fixed. The many worlds view suggests every outcome actually happens. Proposed by Hugh Everett in 1957, the many worlds interpretation sidesteps the problem of wave function collapse entirely. Instead, it says that when a quantum event has multiple possible outcomes, all of them occur, but in separate, branching universes. If a particle could go left or right, the universe splits, creating one version where it goes left and another where it goes right. In this view, reality is an ever-growing tree of possibilities, with countless versions of ourselves living out different histories. While this neatly preserves the equations of quantum mechanics without mysterious collapse, it raises staggering questions. If all outcomes happen, what does it mean to make a choice? And could these parallel worlds ever interact or be observed? Pilot wave theory gives particles hidden paths to follow. Pilot wave theory, also called Bohmian mechanics, offers a more deterministic picture of the quantum world. It proposes that particles always have definite positions and velocities, guided by AEP pilot wave that evolves according to the Schrödinger equation. The strange wave-like interference patterns we see in experiments arise not because particles are smeared out in space, but because this guiding wave influences their trajectories. Pilot wave theory reproduces all the predictions of standard quantum mechanics, but adds hidden variables, unseen details that determine exactly how each particle moves. It's an appealing idea for those uncomfortable with randomness, though it requires accepting non-local effects, where distant events can influence each other instantly. Collapse theories say quantum states can end themselves. Collapse theories propose that superpositions don't last forever. Even without measurement, they eventually decay into a single outcome. In these models, quantum states evolve normally for a time, but have a small chance per unit time to collapse spontaneously. For small systems like atoms, this chance is tiny, allowing superpositions to persist. For larger systems, the collapse happens so quickly that we never notice superpositions in our everyday world. These theories aim to explain why we don't see quantum strangeness at human scales without invoking conscious observers or parallel universes. Experiments are underway to test collapse models by looking for faint, random energy releases that would signal a spontaneous reduction of the wave function. Decoherence explains why quantum strangeness disappears in big objects. Decoherence isn't a separate interpretation, but a physical process that helps explain why quantum effects fade in large systems. Where the quantum system interacts with its environment, air molecules, light, vibrations, information about its state leaks away into countless surrounding particles. This effectively measures the system, destroying the delicate interference patterns of superposition and making it behave more classically. Decoherence happens incredibly fast for macroscopic objects, which is why we never see them in visibly mixed states. While decoherence explains the transition from quantum to classical behavior, it doesn't solve the measurement problem. It still leaves open the question of how one outcome is chosen from the possible ones. The measurement problem still puzzles physicists. At the heart of quantum mechanics lies the measurement problem. How and why does a superposition become a single outcome when observed? The equations describe the evolution of a wave function smoothly over time, but say nothing about the sudden collapse into a definite state. Is this collapse a real physical process, or just an apparent change in our knowledge? Interpretations from Copenhagen to many worlds to collapse theories each offer different answers, but none have been proven. The measurement problem is more than an abstract puzzle. It touches on the nature of reality itself, and on whether the world exists in a definite state when no one is looking. Could human awareness decide reality's fate? Some interpretations, often considered controversial, suggest that consciousness itself plays a role in collapsing the wave function. In this view, it's not just physical interaction with a measuring device that determines an outcome, but the awareness of an observer. This observer effect is sometimes overstated in popular culture, but the underlying idea has roots in discussions by physicists like John von Neumann and Eugene Wigner. While most scientists today favor purely physical explanations, the possibility that the mind could influence fundamental physical processes is tantalizing. Testing it is difficult, but the question lingers. Is reality shaped in part by our act of noticing it? Quantum logic doesn't always obey common sense. In classical logic, statements are either true or false. There's no middle ground. But in the quantum world, logic works differently. Properties can be partly true and partly false at the same time, depending on the context of the measurement. The order in which you measure different quantities can change the outcome, something that never happens in classical physics. Quantum logic reflects the underlying mathematics of Hilbert space, where events aren't just yes or no, but probabilities that can interfere with each other. This departure from everyday reasoning is one reason quantum mechanics feels so alien. It's not just that the world behaves strangely, it's that the very rules for describing it have to be rewritten. The universe might be fundamentally random at its core. In quantum mechanics, some events have no cause that can be predicted in advance, no matter how much information you have. The decay of a radioactive atom, the outcome of a particle measurement, these are fundamentally probabilistic. This is not randomness from ignorance, but randomness built into the fabric of reality. For some, this is unsettling, suggesting that the universe is not a clockwork machine, but a game of chance. For others, it's liberating, allowing for novelty and unpredictability even in a world governed by laws. Whether randomness is truly fundamental or just a reflection of deeper physics we haven't discovered remains one of the deepest questions in science. Quantum physics may bend the rules of space and time. At extreme scales, quantum mechanics and relativity begin to collide, and the results suggest that space and time themselves might not be as fixed as we think. Quantum fluctuations can ripple through spacetime, potentially creating tiny, temporary distortions. Some theories of quantum gravity propose that spacetime is made of discrete units, like pixels in a cosmic screen, while others suggest that time could emerge from deeper, timeless laws. In experiments with entangled particles, correlations appear to transcend normal limits of distance and time, hinting at connections that lie outside our familiar framework. If these ideas are right, then space and time are not the stage for reality. They are part of the cast, shaped by the same strange rules that govern the quantum world. Superfluid helium can flow up walls without resistance. When helium is cooled below about 2 degrees above absolute zero, it undergoes a remarkable transformation into a state called a superfluid. In this state, it loses all viscosity, the internal friction that normally slows a liquid's flow. As a result, superfluid helium can creep up and over the sides of a container, flowing against gravity in a thin film. It can pass through tiny pores that would block any ordinary liquid, and it can circulate endlessly in a closed loop without slowing down. This strange behavior comes from quantum mechanics acting on a macroscopic scale. The helium atoms all fall into the same quantum state, moving together as one perfectly coordinated wave. Superfluid helium shows that quantum effects, normally confined to the microscopic world, can sometimes spill over into forms we can see and touch. Bose-Einstein condensates behave like a single giant atom. Predicted in the 1920s by Satyendranath Bose and Albert Einstein, Bose-Einstein condensate Beck are formed when certain types of atoms are cooled to a fraction of a degree above absolute gamma, 0. At this temperature, the atom's individual wave functions overlap and merge, creating a single, unified quantum state that spans the entire sample. In effect, the whole condensate behaves like one superatom, with all its particles moving in perfect synchrony. BECs allow scientists to study quantum phenomena on a scale large enough to observe directly, such as interference patterns and superfluid behavior. They're a powerful tool for exploring fundamental physics, and their existence is a vivid reminder that matter can take on forms utterly unlike the solids, liquids, and gases we encounter in daily life. The quantum Hall effect creates entirely new forms of matter. When electrons are trapped in an ultra-thin layer and cooled to near absolute zero in a strong magnetic field, they can exhibit the quantum Hall effect. In this state, electrical resistance takes on precise, quantized values, exact fractions or integers that remain stable even if the material has impurities. This effect arises from electrons organizing themselves into new collective quantum states. In some cases, the behavior can't be explained by ordinary particles at all, but by quasi-particles carrying fractions of an electron's charge. The quantum Hall effect has deepened our understanding of quantum mechanics, topology, and condensed matter physics, and it has potential applications in ultra-precise measurement standards and quantum computing. Topological materials host states that can't be destroyed. Topological materials are substances whose electronic properties are determined not just by their composition, but by the shape of their quantum states in abstract mathematical space. One of their most intriguing features is the presence of surface or edge states that are remarkably resistant to disturbance. These states can conduct electricity without scattering, even in the presence of impurities or defects. In some cases, they are protected by the material's underlying topology in such a way that they can't be removed unless the material's fundamental structure changes. These robust properties make topological materials promising for creating stable quantum bits that could resist the noise and errors plaguing today's quantum computers. Quantum tunneling lets particles pass through solid barriers. In classical physics, if a particle doesn't have enough energy to climb over a barrier, it simply can't get through. But in quantum mechanics, there's always a chance it can tunnel right through, appearing on the other side without ever going over. This happens because particles are described by wave functions that extend into and beyond barriers, giving them a small probability of being found on the far side. Tunneling is crucial in many processes, from nuclear fusion in stars to the operation of tunnel diodes in electronics. It also sets limits on how small we can make certain technologies. In microchips, for example, electrons can tunnel through barriers so thin that they cause unwanted leakage currents. Stars burn because quantum tunneling makes fusion possible. The sun's core is far cooler than the temperatures you'd expect for hydrogen nuclei to overcome their mutual electric repulsion and fuse. Classical physics says fusion shouldn't happen there at all. But quantum tunneling allows nuclei to slip through their mutual repulsion and come close enough for the strong nuclear force to bind them together. This process releases the energy that powers the sun and other stars, and without it, the universe would be a much darker place. Tunneling ensures that fusion can occur at the much lower temperatures and pressures found in stellar cores, making it a fundamental enabler of starlight and life. Josephson junctions turn quantum effects into usable circuits. A Josephson junction is made by placing a thin insulating barrier between two superconductors. Quantum tunneling allows paired electrons Cooper pairs to cross the barrier without any applied voltage, creating a supercurrent. This current can oscillate at incredibly precise frequencies when exposed to a voltage, making Josephson junctions valuable in applications like ultrasensitive magnetometers, squid and voltage standards. They're also central components in many quantum computers, where they form the basis of superconducting qubits. Josephson junctions are a clear example of how quantum effects, carefully controlled, can be turned into practical tools for measurement and computation. Observing a system constantly can freeze its motion. Known as the quantum Zeno effect, this phenomenon occurs when frequent measurements prevent a quantum system from evolving. In quantum mechanics, measurement collapses a system into a definite state. If you measure it often enough, you can keep resetting it before it has a chance to change, effectively freezing its behavior. This effect has been demonstrated in experiments with atoms and photons, and it has potential applications in controlling quantum states for computing or communication. The quantum Zeno effect turns the idea of observation on its head. Instead of simply revealing reality, observation can shape and even halt it. Quantum levitation lets objects float above magnets. Using superconductors cooled below their critical temperature, it's possible to make objects levitate stably above magnets. This happens because superconductors expel magnetic fields from their interior, the Meissner effect, and can also pin magnetic field lines in place. The result is a locked position in space, where the superconductor hovers above or below a magnet, resisting being pushed away or pulled down. Quantum levitation has been used in demonstrations of frictionless motion, and while it's not yet common in everyday transportation, it hints at a future where vehicles could glide without contact, powered by E. Quantum effects. Some living things may use quantum tricks to survive. Evidence suggests that certain biological processes may exploit quantum phenomena. In photosynthesis, for example, excitations created by absorbed sunlight seem to travel through plant cells using quantum coherence, taking multiple paths at once to find the most efficient route. Some birds may navigate using quantum entanglement in light-sensitive proteins in their eyes, detecting Earth's magnetic field. Even our sense of smell has been proposed to involve quantum tunneling of electrons in receptor molecules. While these ideas are still under investigation, they suggest that nature may have been harnessing quantum effects long before humans learned to describe them. The early universe was shaped by tiny quantum fluctuations. In the first fractions of a second after the Big Bang, the universe was unimaginably small and hot, a seething quantum field where energy and matter were constantly flickering in and out of existence. Tiny quantum fluctuations in density caused by the uncertainty principle rippled through this early cosmos. These fluctuations were microscopic, but as the universe expanded, they were stretched to cosmic scales. Billions of years later, we can still see their imprint in the faint glow of the cosmic microwave background radiation. They acted as the seeds from which all structure in the universe grew: galaxies, stars, planets, and eventually life itself. Without this quantum noise in the beginning, the universe might have been perfectly smooth and lifeless. Those fluctuations grew into all the galaxies we see. Once the early universe cooled enough for gravity to take hold, the slightly denser regions created by quantum fluctuations began to attract more matter. Over millions of years, these regions grew into massive clouds of gas, which eventually collapsed under their own gravity to form the first stars and galaxies. The distribution of galaxies we see today, not random, but clustered into vast filaments and walls, traces back to those tiny quantum ripples. In a sense, every galaxy in the night sky is a magnified shadow of a quantum event that happened nearly 14 billion years ago. Black holes follow the rules of quantum mechanics too. We often think of black holes as the domain of Einstein's general relativity, where gravity is king. But black holes also have to obey quantum laws. This becomes especially important at their edges, the event horizon, where intense gravity and quantum fields meet. Effects like Hawking radiation, where black holes slowly emit particles, are purely quantum in nature. Understanding black holes fully requires merging quantum mechanics with gravity, something physicists are still working toward. Studying them could reveal new physics, showing how the smallest scale rules of particles connect with the largest scale structure of spacetime. Inflation theory was born from quantum principles. Cosmic inflation is the idea that the universe underwent a brief, explosive expansion in its earliest moments, growing far faster than the speed of light. This theory explains why the cosmos appears so uniform on large scales, while still allowing for small variations. Those variations came from quantum fluctuations in the inflation field itself, stretched across vast distances by the expansion. Without quantum mechanics, inflation would be a very different story, or might not have happened at all. The combination of quantum randomness and rapid growth gave the universe its initial blueprint for all the structure we see today. Dark energy could be the energy of the quantum vacuum. In 1998, astronomers discovered that the expansion of the universe is speeding up, driven by something we now call dark energy. One idea is that this mysterious force is just the energy of the quantum vacuum, the background energy that exists even in empty space. Quantum field theory predicts that vacuum energy should exist, but the amount it predicts is vastly larger than what we observe, making this one of the greatest puzzles in physics. If dark energy is truly vacuum energy, then quantum mechanics is not just shaping the tiny world of particles, but steering the fate of the entire cosmos. Space itself might be made of tiny, discrete units. In our daily experience, space feels continuous. You can move any small distance you like. But some theories of quantum gravity suggest that at the Planck scale, space might be made of indivisible grains, the smallest possible units of length. This would be similar to how matter is made of atoms, smooth on large scales, but fundamentally discrete underneath. If true, this would mean that space and time are not the basic fabric of reality, but emergent properties built from deeper quantum building blocks. Detecting this granularity directly is beyond current technology, but it may leave subtle fingerprints in the way high-energy particles travel across the universe. The universe could be one vast quantum object. If everything in the cosmos is connected through quantum entanglement, then, in a sense, the entire universe might be a single, unified quantum system. This idea challenges the classical view of the cosmos as a collection of independent parts. Instead, every particle, field, and force could be part of one vast, entangled whole. This concept is speculative, but it fits with hints from cosmology, where correlations between widely separated regions of space seem too precise to have arisen without some deeper connection. If true, the quantum universe might be far more cohesive and far stranger than we imagine. Quantum gravity aims to unite all of physics. One of the biggest goals in science is to reconcile quantum mechanics with general relativity, the two great theories that currently describe different realms of nature. Quantum gravity seeks to merge them into a single, consistent framework that works for both subatomic particles and massive celestial objects. Approaches like string theory, loop quantum gravity, and holography are all contenders, but no final answer has been found. A successful theory of quantum gravity would explain what happens at the center of black holes, what happened at the very beginning of the universe, and perhaps reveal the true nature of space and time. Wormholes might be entanglement made physical. Wormholes, hypothetical tunnels connecting distant points in spacetime, have long been a favorite of science fiction. But some physicists propose they could be the geometric manifestation of quantum entanglement. In this idea called ER equals EPR, every entangled pair of particles could be thought of as connected by a tiny, non-traversable wormhole. On a cosmic scale, this could mean that space-time's structure is built from countless quantum links, with wormholes as their visible shape. While still speculative, the concept offers a striking bridge between quantum theory and relativity, suggesting that the fabric of the universe might literally be woven from entanglement. Quantum physics could be the key to understanding everything. Quantum mechanics already explains the behavior of particles, atoms, and molecules, the foundations of chemistry and biology. It underlies the structure of matter, the flow of energy, and even the evolution of the universe. Yet it also leaves huge mysteries unresolved, from the nature of measurement to the unification with gravity. Some physicists believe that a deeper understanding of quantum theory could unlock answers to questions that span all of science, from why the universe exists to whether it could have been different. In this view, quantum physics isn't just one part of the puzzle, it may be the puzzle's frame. Reality breaks its own rules at the smallest scales. The familiar rules of physics, the ones that keep planets in orbit and apples falling from trees, start to twist in strange ways when you look at the tiniest scales of nature. Down at the level of atoms and subatomic particles, matter can behave like a solid object one moment and a wave the next. Objects can exist in more than one state at a time, and outcomes are dictated by probabilities rather than certainties. Even the act of looking can alter what's being observed. This isn't just an odd corner of physics, it's the foundation upon which everything else rests. The fact that reality plays by one set of rules on the surface and an entirely different set underneath is one of the greatest scientific revelations of the past century. Observing a quantum system changes its behavior. In the quantum world, measurement isn't passive. When you observe a system, whether it's the position of an electron or the path of a photon, the interaction required to make that observation inevitably changes the system. This is most famously demonstrated in the double-slit experiment, where particles form wave-like interference patterns when left unobserved, but behave like individual particles when measured. The difference isn't in the particles themselves, but in the fact that the measurement forces them into a definite state. In quantum mechanics, to look is to touch, and to touch is to change. The Heisenberg uncertainty principle limits what we can know. Werner Heisenberg's uncertainty principle tells us that there are pairs of properties, like position and momentum, that cannot both be known with perfect accuracy at the same time. The more precisely you measure one, the less precisely you can know the other. This isn't because our tools aren't good enough, but because nature itself doesn't allow both values to exist exactly at once. The uncertainty principle places a hard limit on knowledge, showing that at the quantum level, reality is not as sharply defined as it appears. Instead, it exists as a range of possibilities until something narrows them down. Wave functions contain the probabilities of all outcomes. In quantum mechanics, the state of a system is described by its wave function, a mathematical object that encodes all possible outcomes of a measurement and the probabilities of each. The wave function doesn't tell you exactly what will happen, only the likelihood of each result. Before measurement, the system occupies all of these possible states at once, weighted by probability. When a measurement is made, the wave function appears to collapse into a single outcome. This probabilistic nature is one of the defining features of quantum theory, replacing the clockwork certainty of classical physics with a softer, more flexible reality. The collapse of a wave function is still a mystery. Physicists can describe wave function collapse mathematically, but they can't fully explain what physically causes it, or whether it even truly happens. In the standard view, the act of measurement forces a quantum system into a definite state. But other interpretations suggest the wave function never collapses, and that all possible outcomes happen in parallel worlds. Some collapse models propose that certain processes or scales naturally trigger the collapse without observation. Despite a century of debate, no one has definitively solved this puzzle. The nature of wave function collapse remains one of the most intriguing open questions in physics. Quantum systems can exist in multiple states at once. Superposition allows a quantum system to occupy more than one state simultaneously. An electron can be in multiple locations, a photon can take more than one path, and an atom can exist in different energy levels at the same time. This is not just theoretical, it's been confirmed in countless experiments. The trick is that superpositions are delicate, collapsing when they interact with their environment. In quantum computers, engineers exploit superposition to perform many calculations in parallel, vastly increasing potential processing power. In nature, superposition is a quiet reminder that reality doesn't have to choose a single option until it must. Particles can become deeply linked across vast distances. Through the process of entanglement, two or more particles can share a quantum state so completely that measuring one instantly determines the properties of the others, no matter how far apart they are. This connection doesn't fade with distance, and it happens without any known exchange of signals. It's as though the particles are part of the same entity, stretched across space. Entanglement is a central feature of quantum mechanics and the basis for emerging technologies like quantum teleportation and quantum cryptography. It's also one of the most mysterious, challenging our classical intuitions about separateness and locality. Measuring one entangled particle affects the other instantly. In experiments, when scientists measure one particle in an entangled pair, they immediately know the result for the other, even if it's light years away. This effect is instantaneous in terms of correlation, though it doesn't transmit usable information faster than light. Still, it defies the idea that objects are independent once separated. The particles don't just share similar properties, they share a single quantum description. This spooky action, as Einstein called it, is now a proven aspect of reality, confirmed in numerous tests that close possible loopholes. Quantum correlations can't be explained by hidden variables alone. Some physicists, including Einstein, once hoped that entanglement could be explained by hidden variables, unseen factors that predetermined outcomes. But experiments inspired by John Bell's theorem have shown that no local hidden variable theory can account for the correlations we observe. Quantum mechanics predicts stronger correlations than any classical theory allows, and nature agrees with quantum predictions. This means the universe is either non-local, allowing influences that transcend distance, or fundamentally different from the tidy, deterministic model classical physics envisioned. Some theories suggest entanglement shapes spacetime itself. A provocative idea in modern physics is that spacetime geometry, the distances and connections between points in the universe, might emerge from patterns of quantum entanglement. In this view, the network of entangled particles acts like a scaffolding from which space itself is built. Remove the entanglement, and the geometry could dissolve. This connection between information and geometry is being explored in theories like holography and quantum gravity, hinting that the fabric of reality might be woven not from matter and energy, but from the invisible threads of quantum information. The universe might be a vast web of entanglement. Imagine every particle in the cosmos, subtly linked to countless others, forming an invisible network that stretches across all of space. In some theories, this is not just poetic imagery, but literal physics. The universe's structure could be a colossal, interconnected web of entanglement. This network would mean that nothing in existence is truly separate. Every atom in your body could, in principle, be correlated with atoms on the far side of the galaxy. The deeper we study quantum systems, the more it seems that entanglement is not a rare exception, but a fundamental feature of reality itself, possibly shaping the very geometry of space. Entanglement can be fragile or surprisingly robust. In most cases, entanglement is delicate. The slightest interaction with the environment can break the quantum link, a process called decoherence. This fragility is a major challenge for quantum computing and communication, where maintaining entangled states is essential. Yet under certain conditions, entanglement can persist far longer than expected, even across large distances or in noisy environments. Some materials naturally protect entanglement, and certain protocols can purify and strengthen it. Understanding how to preserve these fragile connections could be the key to building reliable quantum technologies and exploring the role of entanglement in nature. Virtual particles flicker in and out of existence. Even in the vacuum of space, where no real particles exist, quantum fields are never completely still. Energy fluctuations constantly create pairs of virtual particles and antiparticles, which appear briefly before annihilating each other. These fleeting visitors can have real effects. They contribute to forces between particles, shift the energy levels of atoms, and even affect the behavior of black holes. While virtual particles can't be directly observed, their fingerprints are found in precise experiments, showing that empty space is far from empty. Hawking radiation emerges from quantum vacuum effects. Stephen Hawking's groundbreaking work showed that black holes aren't perfectly black. At their event horizons, Quantum fluctuations can cause one particle of a virtual pair to fall in while the other escapes, becoming real. This slow leakage of energy, known as Hawking radiation, means black holes can eventually evaporate over immense timescales. It's a rare meeting point between quantum mechanics and gravity, and it raises deep questions about what happens to information that falls into a black hole, a mystery still hotly debated today. Vacuum energy may drive cosmic expansion. The vacuum of space holds a tiny amount of residual energy, and according to Einstein's equations, energy has gravity. If the vacuum has energy, it should cause a repulsive effect, pushing space apart. This could explain dark energy, the mysterious force causing the universe's accelerated expansion. The puzzle is that quantum field theory predicts a vacuum energy vastly larger than what we observe. Reconciling this mismatch is one of the biggest open problems in physics. Solving it might reveal new insights into both cosmology and quantum theory. The nature of the vacuum remains a profound mystery. We think of nothing as empty space, but in quantum mechanics, the vacuum is a seething backdrop of fluctuating fields and virtual particles. Its properties influence fundamental forces, particle masses, and possibly the fate of the cosmos itself. Is the vacuum's energy constant, or could it change over time? Is it truly the lowest possible energy state, or just a local minimum? Understanding the vacuum isn't just a matter of curiosity. It's essential for grasping the ultimate structure of reality. Quantum logic can differ from classical logic. In the everyday world, logic is rigid. Something is either true or false, here or there. But in quantum mechanics, outcomes can be partly true and partly false until measured, and the order of certain operations can change the result. Quantum logic reflects the strange mathematical structure of quantum states, where possibilities overlap and interfere. This isn't just abstract theory. It underlies the power of quantum computing, where qubits can explore many possibilities in parallel. It also challenges our most basic assumptions about how reality works at a fundamental level. Reality might be fundamentally probabilistic. Classical physics treats randomness as a sign of incomplete knowledge. If we knew enough, we could predict everything exactly. Quantum mechanics breaks this idea. Even with perfect knowledge of a system's wave function, we can only predict probabilities for future outcomes. Events like radioactive decay or the exact result of a particle measurement are truly random, with no hidden cause. This shift from determinism to probability marks one of the biggest philosophical changes in science, forcing us to accept that uncertainty is built into the universe. Wormholes, white holes, and firewalls challenge our understanding. Black holes are strange enough, but theoretical physics offers even wilder possibilities. Wormholes could connect distant parts of the universe, or even different universes. White holes, the Temerivert cousins of black holes, would spew out matter and energy, but never allow anything in. Firewalls, a controversial idea, suggest that anyone falling into a black hole might be destroyed instantly at the horizon by a burst of high-energy particles, violating the usual picture of smooth keen. Spacetime there. These concepts emerge when quantum mechanics and gravity collide, revealing just how incomplete our understanding still is. Quantum physics may hold the final clues to the universe's secrets. From the tiniest particles to the largest cosmic structures, quantum physics touches every corner of reality. It shapes the behavior of matter, drives the life cycle of stars, seeds the formation of galaxies, and might even determine the universe's ultimate fate. Yet, for all its success, quantum mechanics leaves us with deep, unanswered questions about measurement, unification, and the nature of reality itself. Solving them may require a new kind of physics, But whatever the future holds, the quantum world will remain central to understanding everything that is, was, and ever could be. And so, we drift back from the smallest places in the universe, from the whisper of particles and the shimmer of invisible waves, to the quiet space where your thoughts slow and settle. We've wandered through a realm where reality feels both delicate and unshakable, where what's possible stretches beyond the edge of reason. We've watched matter take on impossible shapes, seen distances vanish in an instant, and learned that even the emptiest vacuum is alive with restless energy. Perhaps some of these ideas will fade, melting into the edges of a dream. Others may linger, like a soft light at the back of your mind, a reminder that the world you wake to is stranger, deeper, and far more beautiful than it first appears. Here in the dark, the puzzles of quantum physics lose their urgency. They don't need to be solved. They can simply exist, small mysteries, infinite and unhurried, drifting quietly alongside you. If you've found calm in tonight's journey, or a moment of wonder, you might choose to like or subscribe, or share this space with someone else. It helps more sleepy minds find their way here, to rest among the stars and questions. For now, the quantum world will keep unfolding without us, softly, silently, in the space between atoms and in the vastness between galaxies. And we can let go, trusting that somewhere the fabric of reality is still weaving itself together in perfect, patient silence. Good night.